Right. Next up is Arkadev.
Okay. Thank you, Casper. This is joint work with Mihal, who's in the audience, Bruno Loff, and Shagnik Mukhopadhyay. So the slides haven't quite kept up with the times because Shagnik is no longer here. He's now a postdoc with Mihal, and this work was done while he was a graduate student at the IFR. Okay, so this is what we will see today. So let me just get into the problem. So I guess you already know by now everything about static data structures, but let me still just go through the drill. So you have, in a static data structure problem, you are given some data that you have to store. You can pre-process the data. There's no computational cost associated with pre-processing. And then you are given a query, and then you have to query. So this is the query. And then given the query, what is the cost of answering this query is the number of probes that you make on your pre-processed data structure. Okay, so this is typically how it goes. So it's very interactive. And here you've made T queries. You've got A1 to AT the answers, and at the end of it, you have to give the correct answer. Okay, so this is the abstract model that we are in. So we call this an SWT solution if you can use S memory cells to store your data after pre-processing. Each of your memory cells contains about W bits, and no matter what the query is from your query space, the query can be answered by probing T cells. So the problem that we will be interested in is a class of problems here called matrix vector product, where the data will always be a matrix, n by n matrix, Boolean matrix, and the query will be sometimes just one vector and sometimes, as we will see, maybe two vectors. And what you have to do is to answer sort of queries that first have to evaluate. So you have to evaluate m times v, so the matrix vector product. And then, depending on the problem, you have to give an answer based on what the matrix m times v that product has evaluated to. So here's an example. One might ask how many rows of this matrix are orthogonal to v, which means that you take the product m times v and find out how many zeros there are in the answer. So this is called the orthogonal vector counting problem. This is a quite well-known problem. It has been asked in other communities, like in fine-grained complexity. Then for this problem, of course, the query is just corresponding to one vector. But now, as I said, sometimes we might have two vectors. So suppose I have another vector. Well, then you want to output a very natural problem. You want to output this vector matrix vector product, right? U times m times v. This is one bit. And this is called the vector matrix vector multiplication problem. Today we're going to be on this. You could define this over any sort of field or any even the Boolean semi-ring, but we will just today look at F2. So all the entries are 0, 1. All matrix operations are over F2. So what are our results? These are our results. So what we show is that any randomized data structure will need at least these many queries. So notice that this is not crossing, making any major breakthrough in the sense that it's not crossing the well-known barrier of static data structures because you still get only epsilon n, where n is the size of the query space. Okay, so this is the best possible kind of lower bound that you can get short of a breakthrough. But what's interesting is that first of all, we get this for two interesting class of problems, and secondly, the bounds are average case. So even if you want to make slight advantage over random guessing, so read this in this way: there exists some epsilon such that if you do not make about epsilon n many queries, then you can't compute the vector matrix vector with advantage better than 2 to the minus epsilon n. So there is some fixed epsilon, and the same thing is here for the orthogonal vector counting problem. So here I've assumed just to get an average case bound, say the problem was to count if the number of orthogonal vectors is 0 mod 3. Okay, so then you can, by just giving a constant answer, you can get 2/3 advantage, and this is just saying that just to beat that naive probability, you will have to expend a lot of query time. So these are the two results, and actually what would be more interesting for particularly this crowd is the way we prove these results, which is via a lifting theorem for a certain communication game, which I'll soon come to. So these are just two concrete results that we get. So first, also note that the upper bound here is for let's say the orthogonal vector counting problem. The upper bound is n squared by w log s, and let me just quickly sketch that thing. So you have this matrix M, n cross n, and now I'm going to just divide it into blocks of size r, let's say. We have this U. So now again, this can be divided into size r. That's the total number of blocks is n by r. And now you can look at all possible pre-computations, linear combinations of these r columns, right? For every block, I can pre-compute them. So for each one of them, I have 2 to the r linear combinations possible, and each linear combination is an n-bit vector. So if I have w cells, I can store them in n by w number of cells, because each cell is worth w bits, and there are such n by r blocks. So this is my space needed, right? So log of s is roughly about r plus some small order terms. Okay. And the number of queries that I need to make is now, when I get a vector, I know I read this r, each of these blocks, and I know, correspondingly here, which linear combination do I need. So I will actually need to query about n by r times n by w, right, which is n squared by wr, which is about n squared by w log of s. I hope that's clear. So the upper bound is n squared by w log s always, because I can compute the entire matrix vector product following this thing. So if w is n, which is not the typical range that you look at data structure, w is log of n, but in some models like the external memory model, w can be large. So when w is n, this shrinks to epsilon n by log s. And in our lower bound as well, if you put w equals n, you get exactly about n by log s. So for large word size, this is tight. This can't be improved. Okay. So let me also state some related results very quickly. So in a seminal work, Miltersen, et al., Miltersen, Nissan, Safra, and Wigderson, they considered again a matrix vector product problem, where now you're given a matrix which you pre-processed as before, then given a vector. You want to find out whether the m dot v is exactly equal to 0, which is also a subspace membership problem, and that's why they called it the span problem. And they were able to show that for that, the number of queries needed would be n by log s. This is the deterministic lower bound. This actually also works for one-sided error, but it does not work for two-sided error for good reasons. And this method that they used, which I will come to very soon, called the Richness technique, does not seem to quite work for vector matrix vector product or orthogonal vector counting. So in another very recent work, Casper and Ryan showed that for the vector matrix vector product, in fact, you can solve it quite efficiently, because naively you would think that you need n squared, but they showed that this can be done in n to the 3/2 over square root of w. And I think later today we are going to hear more about this talk by Chakraborty, et al. But however, these are over the Boolean semi-ring. Okay, so these don't work for over F2, which is what we consider. So it's still conceivable, and I think it's an excellent candidate to show an n square lower bound when the word size is about log n. So n square by log n lower bound even for polynomial data structure. We don't have any evidence that such a lower bound is not possible. Okay. So again, these are our results. So how do we prove this? As I said, so we prove it via a very general technique called lifting theorems, and the connection here is through communication complexity. So there is a well-known connection that was initiated in the work of Miltersen et al. In the first paper, showing that there is a model independently interesting and also connects to data structures. So if you prove lower bounds on that asymmetric communication model, that implies lower bounds for data structures. And we revisit that model, and what we are able to show is the simulation theorem both for deterministic and randomized. So this is the new part, and this is, I think, interesting, the most interesting aspect of the work. So let's quickly go to the asymmetric model. Okay, so this, as I said, was introduced by Miltersen et al. Here, unlike in the standard communication model, the emphasis is one of the players is going to have a long or large input, and the other player is going to have a short input. Okay, and because there's this asymmetry in the size of inputs, there is naturally going to be budgets that are going to be placed on how much a player can communicate. Because if, for example, Bob, who has a very small input, is allowed to communicate a lot, then Bob can just transfer all the bits that he has to Alice, and then the game is over. So you have to constrain Bob in a meaningful way, which says that Bob is allowed to send only B bits, Alice is allowed to send A bits. Because Alice has a larger input, typically A would be much larger than B. And when there is a protocol that obeys, that conforms to this budget, then we say that that's an order AB protocol. Okay? And when we want to prove a lower bound, well, we say that either Alice has to send A bits for solving that problem, or Bob has to send B bits. And the notation I will use here is that in such a case, I'll say that the complexity of the problem is omega AB. So there are constants here hiding. So I'm just saying loosely that I'll say this is omega AB, has omega AB complexity. So how does this connect to data structures? Well, the connection is actually quite elegant and simple. So suppose you had an SWT solution in data structure. The claim is it gives rise to this efficient protocol in the asymmetric model. So where Alice would send TW bits and Bob would send T log of S bits. Why so? So this is just clear from just visualizing what's going on. So now I'm going to use, so Alice is just going to simulate the data structure, and Bob is going to simulate what the query algorithm would do. And so each time Bob queries, Bob is querying a particular cell, so Bob sends log of S bits, and then gets back W bits, which is the contents of those cells. So if this occurs for T rounds, then of course, in total Alice sends TW bits and Bob sends T times log of S bits. So if you can prove a lower bound, on these things, then you get a lower bound relating TW and S. Okay? And that's what we are going to do. Okay? So what this original paper did was they introduced a richness technique, which I will get to if there is time towards the end of my talk. And they proved results using the richness techniques for a variety of problems. But what we are going to do today is to prove this using a generic technique, which is generic, but it will only work for this sort of matrix vector product class of problems that we are considering. Okay? So what would be the setting? So the setting would be of these composed functions. Now typically in block composition, of course, you have Alice has k inputs, x1 through xk, and Bob has y1 through yk, and then you have some gadget g that is applied to each instance xi, yi, and then you compute some function of applying the gadget. But here, on the other hand, because of the asymmetry, what we will have is, there will be one input just for Bob, whereas Alice would get p independent inputs, and then we're going to apply this gadget, where the gadget would be applied with the same input y for Bob, but with various different inputs for Alice. Okay. And then, as before, this would give rise to p bits, and we can apply a function of those p bits. Okay. So in particular, what we will consider today is, you could do this for any gadget G, but for matrix vector product over F2, what we will look at is when G is the inner product. Okay, then you get exactly F composed with matrix vector product. And so this is what you have, because this is the matrix P rows, and you take the product, and this product is basically what G is. So what we can show is the following. Okay, first let me show you an upper bound. So what should we expect? So there's a very naive generic way to solve problems of this kind, which is by using parity decision trees. Okay? So I claim that for any f, f of matrix vector product can be solved where Alice sends the parity decision tree complexity of f times n, and Bob just sends the parity decision tree complexity of f. Okay? And it's actually quite simple to see why this is the case, is because of the fact that there is just one y. Okay? So Alice is given x1 through xp, Bob is given y, and now they want to use a purported parity decision tree that exists for f to solve this problem. So they would just simulate the parity decision tree. So at each point, a parity decision tree asks a query, and the query it asks about is on the input bits to f, but the input bits to f are generated by taking this matrix vector product, right? So it asks a query on these bits, and well, you can just view it differently. You can just think of this. This is like a vector matrix vector product. So you can first evaluate this, and this Alice can do, of course, by herself. And when she evaluates this query, she gets an n. So this is 1 cross p vector. So she gets an n-bit vector. So she can evaluate the query on her side, and then just transfer the result, which is an n-bit vector, to Bob, and then Bob computes the inner product with y and sends back the answer. So each query in the decision tree, the parity decision tree that you have, can be simulated by Alice doing the corresponding bitwise XOR of her matrix, okay, and then transferring the result to Bob, and then Bob giving back the answer. Okay, so in total, therefore, Alice is going to use, and they do this for each query, traversing down the parity decision tree. So for each query, therefore, in total, therefore, Alice communicates the parity decision tree complexity of f times n, and Bob just communicates parity decision tree complexity of f. Okay, is that clear? Okay, so this is a very natural upper bound, and what we show is that this is the best that they can do in general. Meaning that either Alice in any protocol for this game, either Alice will have to communicate these many bits, exactly matching what the upper bound is, or Bob will have to communicate that many bits. Okay. So, and this also actually turns out to be true for the randomized model. So we can not only prove a deterministic simulation theorem, but the same proof with a bit more work extends to the randomized model as well. So what's the main ingredient of our argument? So the main ingredient is, as in various works in lifting theorem, what we do is, given a protocol which is of this form, where Alice sends at most c times n bits and Bob sends c bits, we can take this protocol and extract a parity decision tree for f with about cost 100 times c. Okay, so if both if I knew that Alice sent C times N and Bob sent C, then I can extract a parity decision tree for F of cost at most 100 times C. And therefore, if the parity decision tree complexity of F was large, then these things should be large. Okay, so this follows the same template in this sense as the other lifting theorems. But of course, the difficulty here is somehow parity decision tree has to enter in my lifting result, right? Because I can't hope to get a normal decision tree lower bound. Okay, so that's the main sort of mysterious thing. The other thing is, of course, there are this, somehow I have to consider also that Alice and Bob have got different budgets, and Bob has, more importantly, Bob has just got one input. Okay. So I wouldn't have time to get into this the proof of the lifting theorem, but in all these lifting theorems, you sort of maintain an invariant, right? You want to say that, okay, you're going down the protocol tree, and at each point you maintain a rich rectangle, a rich enough rectangle that sort of allows you to query minimally, and whenever you don't query, when you stop, you can still say that the things that have unqueried, they all have sort of a representative in the rectangle that you have maintained, right? This is what, you have to choose your richness measure appropriately so that you can make this argument happen. So usually what has been done in lifting theorems, for example, in the BPP lifting theorem of Goose, Pitassi, and Watson recently, is that they look at the minimum, the blockwise minimum entropy should be large. So here, the rows are 0, 1 to the np. So these are all matrices of the type P cross n, and Bob has an n-bit vector. So you might think that, can we apply a similar technique here? Would this measure suffice? Well, first of all, as I said, somewhere the parity decision tree has to enter, and these measures naturally work when you are trying to simulate an ordinary decision tree. So this doesn't work, but a very natural adaptation of this works, which is that instead of looking at minimum entropy blockwise, I look at a linear min entropy. So what is linear min entropy? This is the novelty in the work. So the linear min entropy is the following. So consider, so now I have to look at, somehow I have to look at affine subspaces. So consider the affine space of all possible entries here, such that if Q is a query vector, Q multiplied by those matrices give me the vector U. Okay, so this is a set of all matrices such that Q times that matrix is equal to this vector U. Okay, this is the affine space that I'm looking at. Okay, so I have some A subset of this, and then I said the linear min entropy of this is the largest eta, such that if I look at any extension of Q, Q prime, which are still, so these are a fresh set of queries, but they are still linearly independent of Q. Okay. Then if I look at Q prime dot X, so X is a possible P cross N matrix. Okay, so if things were perfect, then this would be completely random, right?
Sorry, please slow down just a minute. So
sure.
Q is?
So Q is my query vector. So the Q is the set of queries that I've made so far. Okay, and somehow I've been constrained to fix them to something. Okay, now I'm looking at a fresh set of queries Q prime, which I have not made, and I want to be sort of rich with respect to this Q prime. Okay. So
Q is like the query of the data structure, or of like the parity decision tree?
Oh, the parity decision tree. Yeah.
Okay.
Yeah.
So query.
So you're going down the.
It's a very defined vector. It's a vector.
Yeah, it's
a bunch of vectors.
So Q is a bunch of vectors.
Okay, so subspace of.
So Q is of this form. So maybe you've made R queries. So it's an R cross P matrix. So each query is like a it's a p-bit vector. So A is the set of A is the current set of matrices that satisfy the following property. When you apply this Q on A, you get this fixed vector U. So Q is just like in ordinary decision trees. You query a particular coordinate. Q corresponds to a linear coordinate. Okay, and you queried it, and you want an answer, right? So that the set of possible answers that you've got is U. Okay, so these are the set of matrices which, when queried by Q, will conform to the set of answers that you have seen, and you're maintaining that, right?
Sorry, so U is a matrix?
U is a vector.
Okay, but then Q.
Q times, so for every x in A, Q times x is equal to U.
So A is a matrix?
Sorry?
Sorry, so A is a matrix?
A is a set of matrices.
So it seems like it is.
Oh, I
What?
So it seems like the natural generalization of the
So
unit.
all I'm saying is,
yeah, could you write down the definition of
so for all x in A, Q times x is equal to U. And U is in 0, 1 to the R. Yeah.
So A is a set of vectors, not.
No, A is a set of matrices.
But then how it can be equal to U if you multiply by a matrix?
You think about there is just a vector.
Right? No. I mean, so you.
U is a matrix, yeah?
Yeah.
So you multiply matrix by matrix and you get a vector.
Oh. Now you're.
no, Q is a matrix?
It's
fine.
Well, it's okay.
Okay, I think the point is that you think now about the matrix as a vector. I mean, it's a long vector, right?
I think it's just. I think it's right because. I mean, you're just getting.
A is the subset of a subspace, right? So it just
No, so you're right. So U is a U is a matrix.
Oh.
U is a. I'm sorry. U is.
Actually, the answer to the phrase Q is the vector U.
U is a matrix. Sorry.
And I have the next question, sorry. And how we use A in the definition of the entropy?
So this is what I'm saying. So if you choose X, X is sort of chosen uniformly at random from A. Okay, so the condition is if I look at every Q prime which extends Q in a linearly independent way. So Q prime is another set of queries, each of which is linearly independent from Q, right? And if you look at when X is chosen uniformly random from A, and you look at Q prime dot X, yeah, that's going to give you Q prime times n bits, right? Because you're looking at Q prime dot X. Now, if you look at this distribution, the minimum, the largest min entropy it could have had is without the zeta, right? Q prime times n. Okay, and I'm saying that you should have at least eta times the largest eta such that you have eta times Q prime times n. Yeah. So, and this is sort of the linear analog of block min entropy, right? So each Q prime sort of defines a block in the linear after a linear transformation, and I'm saying that corresponding to that linear block, the min entropy has to be large. This has to be true for every block which is linearly independent of the set of queries that you have seen so far. So, okay, so this is the invariant that we maintain, but that's on this side. Okay, but for the other side, which is the smaller side, actually it turns out that side is simpler to maintain. So all we need is largeness. So for on Bob's side, what we need to maintain is just that the min entropy has to be large. Okay, which is a bit different from the usual lifting theorem, where you sort of maintain this careful block min entropy with respect to the smaller side. So let me just quickly go through. So I wouldn't have time to talk about the lifting theorem more, but let me just give you an example why this sort of thing can be more powerful than the Richness method. So the Richness method, just to quickly recap, it sort of says the following, that if your matrix is UV rich, which means that your original function had this property that there exists some set of V columns in which in each of these columns there were at least U many ones, then you call that such a matrix UV rich, and you essentially prove that in an AB protocol, if your matrix to start with was UV rich, then you will have a large rectangle of this kind, and if you didn't have a rectangle of that kind, that would just show that there is no AB protocol. But the important point here is that this method is sort of a bit too powerful in the sense that it ends up proving not only deterministic lower bound, but it also proves randomized one-sided lower bound. Okay, and here's a function which will have large deterministic complexity, but not randomized complexity, and therefore, because of the fact that I said before, richness cannot be used as it is to prove this bound. So the function that we'll look at is a promised function where you have 2n bits, and for the inputs on which the function evaluates to 1, it is promised that on all odd indices you have 0, and on the even indices you have at least n by 10 ones. And for inputs on which the function evaluates to 0, the even indices have all zeros, but on the odd indices you have at least n by 10 ones. And now this function has a very simple zero error parity decision tree complexity, because at random a parity decision tree would, in fact, just not even a parity decision tree, an ordinary decision tree complexity, because at random, if you sample two consecutive indices, one odd and one even, then you're either going to, with high probability, see 1, 0 or 0, 1, right? And seeing either of which, you know what the promised input was. So it's easy to, just by two queries, to separate the two promised set of inputs. So it has a small zero error query complexity, and therefore, if you lift it with this matrix vector product, that thing will have a small zero error protocol of cost order n, order 1, right? Because for each query you have to send n bits to Bob, so that's why you get an order 1, and Bob sends back this one bit answer. And therefore, richness would fail to give you anything better than that, because richness ends up proving lower bounds also for, as I said, for one-sided error. However, what we can show is that with this promise, the deterministic parity decision tree complexity of this function is large. It's maximally large. You will need n queries. Okay? And therefore, by using our lifting theorem, we can show that this function would have deterministic lower bound of omega n square. So either Alice has to send omega n square bits, or Bob has to send omega n bits, and this sort of maximally separates it from richness. Okay. I think I'm out of time. So let me stop here. Thanks.
Any questions?
Main barrier to the n squared that you mentioned before?
Oh, for data structure? Well, I mean, using this communication complexity approach, we cannot go beyond the log of the query space, right? Because was that your question?
Well, I thought you said for word size, for small word sizes, there's a possibility of getting something better than absolute.
No, not through this method. I just meant that it is plausible that is the true bound. because this still uses communication complexity, it won't be able to go beyond that.
I'm not sure it makes a lot of sense, but can you please go to the definition of this entropy? So here is so if there is some set of queries, not necessarily linear, some set of queries, and the decision tree will consist of these queries, okay? So not linear, just abstract. And you replace it by, instead of Q prime, every Q prime that does not logically follow from what you have queried so far. And the same property holds. So
you're redefining that, or?
So
it,
just extending this
okay.
to,
Okay.
so your proof will go through?
No.
No.
I don't think so. We can talk offline. Somewhere in the proof we use linearity further. More than one place actually.
So in this proof you didn't use that whatever Alice answers, it's like memoryless. It only depends on what, like in data structure lower bound, in data structure model, Alice answers only depend on what Bob sends in the last round. So
right. That's the bottleneck of using this communication model. That's true.
So are there any communication models that even try to formalize that?
So I'm not sure, but watching has had some model that sounded like, did it?
It cannot beat this log of the query size. In dynamic model you can get one more.
It's for dynamic.
Yeah, but not more than that.
Yeah, so otherwise I'm not aware of. So somehow you have to, what you're saying is that Alice cannot be an active player. Alice has to be, you have to have a game in which Alice is very passive, right? And that is, well, doesn't seem like there is a clean model to capture that. The cleanest model is possibly the cell probe model itself.
Oh, I think Arkadev again.